All right, we're going to go ahead and get started. Just a reminder to drop your projects off in the back of the room. Okay, so today is going to be a fun day, which is that we've spent the last few classes talking about some of the math behind probability, what probability density functions are, things like that. And so finally, today we're going to get to the point, which is how we can actually use these tools to do the thing that we care about in this class, which is doing inference about populations. And so, right, hopefully today, like some of the stuff that we've been doing will finally make sense. We actually get to apply this to do something useful. Okay, so just to remind you about the goal here, right? One of the most common types of things that we want to do in statistics is make some kind of inference about the means of a population, right? So we have a sample mean that we're measuring in the data we actually collected, and then we want to make some kind of guess about what's going on in the population. And the two kinds of guesses we often want to make is either something like estimating what the population mean is, or maybe more importantly, estimating a confidence interval for the population mean. And we also might want to test whether this mean differs from some null mean. And the null mean is often zero, although it doesn't have to be zero, but right, we have some null hypothesis about what a non-interesting mean would be in the population, and we want to test whether or not we think our mean is interesting or not. Is it different from this null mean? Right, so what we have is our data. That's, again, something that we know exactly, and we're going to want to make guesses about these kinds of things in the population. So we've already talked about ways to do this, right? And so the ways we've talked about so far are basically kind of simulation based, right? So we could generate samples from a null hypothesis, for example, either through explicit simulation or through permuting our data set. We could also try to generate confidence intervals through bootstrapping procedures, which again is a sort of a type of randomization. And these tools we talked about so far are great, and they're very general, right? They make very few assumptions about the data, except that every data point is an independent, unbiased sample. But now that you've done this a bunch of times, you should have started to notice that the answers we get with these methods often look kind of similar. So here's an example of this. So let's say we're going to run some simulation here about collecting data from this population distribution, for example. So this is a uniform, standard uniform distribution, right? So this is a distribution just that takes values like between 0 and 1. So we're going to simulate taking data sets of 3 samples. And what we're going to do is then look at like 2,000 of these null data sets, right? So what we do is we take 3 draws from this uniform distribution. We take the mean of those 3 numbers, and then we repeat this 2,000 times. So we end up with 2,000 means, and you'll get something that looks like this, right? So the mean is usually around like 0.5. Sometimes it's close to 0 and 1, right? But it's like usually somewhere in the middle. We could also imagine maybe our population distribution looks like something else. Maybe our population distribution is exponential, like this. And we could do the same thing. So we're going to take 3 samples from the exponential distribution, average them together to get one number, and then repeat that 2,000 times. And we'll get this kind of blobby thing, right, that the means are usually right somewhere here towards the left. Sometimes we just happen to get 3 samples that are out in the tail. We could also do this. We could imagine that the population distribution is normal. And again, we're going to draw 3 samples, get the mean of those 3 samples, repeat this 2,000 times, and here's a histogram of those 2,000 means. And so you can see, even though the population distributions are very different from each other, the distributions of the means of the data sets start looking kind of similar. Like they all have this kind of peak and they fall off. They still look a little bit different, right? But they're sort of qualitatively start looking similar. And the similarity actually gets a lot stronger if we start making these data sets bigger. So if instead of getting data sets of 3 sample points, if instead we switch to getting averages of 10 numbers, we take 10 samples, get a mean of those 10 numbers, that gives us one number, and we make a distribution of those 2,000 means. In all of these cases, we get things that do look Again, they don't look totally identical to each other, but they're starting to all have this very similar shape. right? So even though the distributions, the population distributions here are very different from each other, when we start looking at the distribution of sample means, that distribution starts to always have this kind of property where it's kind of centered around some number and then falls off away from that number. Yes?
If you take the average of 10 random samples,
Mm-hmm.
then what does it mean that you collect 2,000 of those averages? Because then isn't that just the same average?
So we draw 10 random samples, we get their mean.
Oh, you do that
Then we
with
draw
samples?
another 10 random samples,
Okay.
get their mean, draw another 10 random samples. Yeah, so we're again, this is not something we'd actually do in real life, but this is just like simulating what our data sets could look like. If we collected a data set of 10 people from this distribution, what would its means tend to look like? And this, right, these are sort of the likely places where the means would fall just by simulation. And so what's happening here is that these, no matter what the population distribution looks like, the distribution of the means in our samples, right, that's the thing on the right, actually always starts to look like a normal distribution. And so this is one of the more famous theorems in statistics, which is called the central limit theorem. And it's kind of this like law of large numbers idea, and it's specifically about means of samples, right? So this only applies if we are computing a sample mean, and we're interested in how the sample mean is distributed. And so we're not going to like prove this in this class, but the central limit theorem tells us a few different things, all of which are super useful. So okay, so what this applies to is the mean sampling distributions. What that means is we are looking at a probability distribution of the sample means, right? Which means we're going to draw multiple data points from some distribution and average them together to get a single number. And this is talking about how that single number is going to behave, right? That if we took lots and lots of samples, does that single number, that mean, where does that tend to land? So the first thing that it tells us is that this sampling distribution gets tighter and tighter around the true mean of the population as you get more samples. This is not really that surprising. We already kind of assumed this when we were doing things, right? That we talked earlier about how the sample mean is an unbiased estimator of the population mean, right? And so the sample mean is sort of going to be right on average about what the population mean is, and our estimate will get better and better as we get more and more data points. Right? So I think this fits pretty well with our intuition that as our sample gets bigger and bigger, the mean that we measure in that sample is going to get closer and closer to the mean of the population distribution. Okay, the next thing it tells us, which is definitely not obvious, is that this sampling distribution starts turning into a normal distribution, right? So what this means, again, the distribution we're talking about here is the distribution of these sample means. And so what it says is that if you do this little simulation like we were doing here, right, where we imagine computing lots of sample means by taking different sets of samples from our population, those sample means, the distribution of the sample means, it turns into these normal distributions. Right, so this is quite interesting, and this is based, like pretty much the entire reason why we've been talking so much about normal distributions is because no matter what our population looks like, if we want to make inferences about sample means, the sample means are going to be distributed as normal distributions. And so, there's of course like lots of asterisks on here, like of when this actually, like how big n has to actually get for this to be true and things like that, right? We showed that if n is only 3, then this is like not super true, right? That second thing there is not that normal, but right. But at least in like reasonably sized data sets, this is going to be approximately true. And so with this, what we're going to do is the rest of the class today is talk about building up a theory about how to do statistics on these normal distributions, and we're going to continue doing this over the next couple classes as well, right? Because if we have that tool, it can apply to almost any population distribution, right? The tools we're building are going to work whenever our sampling distribution of the mean is normal, which is by the central limit theorem, which is basically true almost any time as long as n is reasonably big. The fourth thing that it tells us, which is also definitely not super obvious, is it tells us how it tells us how this normal distribution converges towards the mean. Right? So point 2 there is telling us that as n gets bigger and bigger, the sampling distribution is getting tighter and tighter. It's going to be more and more unlikely to get a sample mean that's very far away from the population mean. Right? So these sample distributions are getting thinner and thinner. Right? The range of likely sample means is going to get smaller and smaller. And what the essential limit theorem tells us is that the rate at which things get smaller is basically the square root of n. So as we, if we make n 4 times larger, we're going to end up with a sampling distribution that's half the width that it was before, right? And so what this tells us is that we can basically estimate how big of an n we would need in order to get a certain degree of confidence in what the population mean actually is. So yeah, we're going to go through the rest of the class today to go into each of these things in more detail, right? But this is basically the foundation for most of traditional statistics, is the fact that this is true, that we can make this assumption that the sampling distribution of the means is approximately normal and has this standard deviation that's going down with the square root of n. And so again, you can just choose to, the way we've been doing things so far, we've just ignored this fact and just simulated out things just brute force wise, right? Which is fine. And if you actually look at the things we've been simulating, and you're going to do this in the lab today, the things we've been simulating actually have been basically normal distributions with this standard deviation, right? And so we can sort of skip the steps of actually doing the permutations, at least in some cases. Okay, so the shape of the sampling distribution is going to depend on the size of our sample. And so at least if we know what the population standard deviation is, and again, any population distribution has a standard deviation. It doesn't have to be a normal distribution, right? We can compute the standard deviation for any distribution. If we know this population standard deviation, and we know how many samples are in our data set, then we can compute what's called the population standard error. And so the standard error here is the standard deviation of the sampling mean. And by the essential limit theorem, the standard error is simply the population standard deviation divided by the square root of n. And so so if the population is normally distributed, then this sampling distribution is exactly normal. If the population is not normally distributed, then this sampling distribution just is becoming more and more normal as n gets larger. That's what the essential limit theorem is telling us. And so the sampling distribution has the mean of the sampling distribution is this, so we're denoting the mean of the sample as x bar, and the standard deviation is the standard error, right, which is telling us how much we expect this sample mean to vary if we had drawn a different sample. So we want to be really careful here about, we're now talking about two different distributions, and this is probably what the most common place where people get confused in statistics is that these two distributions are not the same thing. So we want to be careful about what we're talking about. So one distribution we could talk about is the population distribution. So this is talking about if we just draw a single sample from our population, where is that sample likely to live? And so that's the blue line here, right? This population distribution is something that we never actually see. It just describes the likelihood of getting any particular sample at any particular value. But now we're also talking about this other distribution, which is this sampling distribution. And here we're talking about the sampling distribution of the mean, although it could be for other type of descriptive statistics too. And so the sampling distribution of the mean says if we draw a data set, say we take a data set of 25 points and compute the mean of those 25 points, then what values is that mean in our sample likely to have? And so this is the stuff, the essential limit theorem is talking about the second thing, the sampling distribution of the mean. The sampling distribution of the mean is usually going to be a much narrower thing than the population, right? Because we're averaging together 25 numbers. And the sampling distribution of the mean is this thing that the standard error applies to, right? This sampling distribution of the mean has a standard deviation, which is the population standard deviation divided by the square root of n. So as n gets bigger and bigger, this sampling distribution of the mean gets smaller and smaller and smaller, right? If we have a very, very large sample, then almost every sample will have exactly the same mean, which is right at the population mean. But the population distribution has nothing to do with sample sizes, right? That's just the chance of drawing a single sample from our original population. Yes?
Sorry, I'm like still waking up. You said that as the sample gets larger, that distribution gets narrower?
The sampling distribution of the mean gets narrower,
Okay.
yes. That's right. And right, the essential limit theorem tells us specifically how fast it gets narrower, which is this 1 over square root of n term.
Okay.
And so, right, and again, the general intuition that it gets narrower should make sense, right? That if we take very large samples from our data set and compute a mean on that very large sample, that mean should be super, super stable, right? We think about like in terms of bootstrapping or something, right? It shouldn't depend that much on individual values. Even if we get a couple weird numbers in there that are kind of unlikely in the population, it's not going to mess things up too much, right? And so the sampling distribution of the mean tells us that, so in this example here, right, it tells us that if you draw 25 numbers and take their mean, that mean is going to be very tightly centered around the true population mean, right? You may be, in this example, you're off by maybe like 10 at most or something. Okay, and so the reason the sampling distribution is so interesting to us is that our goal often is to try to say something about the true population mean based on the sample mean that we got, right? And so this red thing is also not a distribution that we actually see, right? Neither of these things are things we actually see. The red distribution here is telling us something about if we did many separate experiments, what kind of means would we get in our experiment? And so we only ever get to see one sample mean, and we want to make some kind of guess about what population means are likely. And so by the essential limit theorem, what that tells us is that if our n is really big, then our sample mean is probably a pretty good estimate of the population mean. And so the sampling distribution of the mean tells us something about what population means were likely to have led to our sample mean. And so that lets us find mu, right? Not exactly, but this can let us get things like confidence intervals for where the population mean is. It's also going to let us do null hypothesis testing, right? So we'll be able to write down here if the null hypothesis is true. We'll write down what sample means are likely, and we can see if the sample mean we got is actually one of those or not. Okay. I'm going to do one more example here of essential limit theorem stuff. So in this example, on the top here is the population distribution. So this population distribution is just a totally uniform distribution. And so what we're going to do here is draw a sample. So let's draw a sample of size like 10. So we're going to draw 10 values from this uniform distribution, right, which just means we're totally randomly picking numbers. And then we're going to take the average of those 10 values to give us a single mean. So let's do that. We pulled out our 10 little dots, average them together, and the mean landed right here. We can do that again. We're going to draw out a different set of 10 dots, take their mean, plopped over there. We can do this again, draw out a different set of 10. Okay, now we're going to speed things up a little bit. Let's just do 50 of these, right? So we're going to 50 times draw 10 things, take their mean. Okay, many things are happening. And so this thing that we're building on the bottom is the sampling distribution of the mean, right? This thing that we're building on the bottom is telling us where the mean tends to land. When we take 10 values, take their mean, where does that tend to end up? And so the samples we've run so far, it never ends up like way over here, which kind of makes sense. You'd have to get really unlucky to get 10 draws that are all over here, right? It usually ends up somewhere in the middle here. And so what we could actually do with the essential limit theorem, so the essential limit theorem tells us that this sampling distribution at the bottom here should be normally distributed. It should have a mean, which is the population mean. and it should have a standard deviation, which is the standard error, which is the population standard deviation divided by the square root of 10 in this case. And so we can just draw out what that normal distribution is, which looks like this, right? And so it's not exactly accurate just because, we'll have to do some more samples maybe to get this exactly right. But, right, so what this tells, so that red line there is the essential limit theorem theoretical version, right, which says that if we take samples of 10 items, take their mean, that mean should be normally distributed here. It should land, right, it should be centered on the true mean of our distribution and have this particular standard error. Right, so we could also, so the essential limit theorem also predicts, so if we go from, let's say, instead of 10, let's up this to 15 samples, right? So if you switch back and forth between these, this is 10 samples and this is 15. The essential limit theorem predicts that this thing should get narrower as n goes up, right? We could also go down the other way, right? It predicts if you only take like 2 samples, right, then you should look something like this, right? The mean of 2 samples could land almost anywhere here, but we're very uncertain. If the mean of 15 samples should only land in this narrow range, right? And we could test that to see how good it's doing. So yeah, prediction seems pretty decent here, right? That most of our values are landing inside where the essential limit theorem is telling us. Now the cool thing about the essential limit theorem is that, right, this works for any population distribution. So let's smush our PDF around a little bit. And remember, the area here just always has to equal 1, but we can just sort of smush it around however we want, right? So let's smush it around to, let's do something kind of weird like this. So here is a somewhat weird distribution, population distribution. It's definitely not normal. It's not really, it's actually a beta distribution, which we haven't talked about. And so, but the essential limit theorem says all we have to do here is measure the mean of this population distribution, measure its standard deviation, and then we can write down what the sampling distribution should look like, which is that it should have the mean, which is the population mean, and it should have a standard deviation, which is the standard error, which is the population mean divided by the square root of n. Right, and so we can do our draws here and see, right, and it does a pretty good job predicting where the means should end up. Yes?
What are you pulling from when you're determining standard deviation? Are you doing that for like each, like you're getting the mean for each sample set that you're pulling from and calculating the standard deviation for that? Or are you like looking at the standard deviation of the distribution of it?
So the mean and standard deviation I'm talking about here are of this population distribution up here. So we can compute the mean of that population distribution, which is like, doesn't involve sampling at all. It just involves like calculus of computing that, right? But you can think about it as like, it's the mean you would get if you had like an infinite number of samples out of here or something, right? So from this mathematical function that describes this line here, we can compute where the mean is, and we can compute what the standard deviation of this thing is. So those are things that we like calculate out with, there's no like sampling involved or there's no error involved, right? We can just, from the mathematical function that describes this thing, we can calculate out what those numbers are.
I thought we don't know the population. Like,
Yes, so, so one thing I'm glossing over here is that this requires us to know the population standard deviation, which we don't know. So we're gonna fix that next week, but.
the central limit theorem requires you to know that?
The central limit theorem requires you to know that, that's right. So the population mean actually is usually not that big of a deal because we, often what we're going to do here is have the population we're going to compare against is like a null distribution where we can know what the mean is because it's something that comes from a theory that we have. But yes, there is a big problem here, which is that we don't know the standard deviation of the population, and so we're going to. The test we're going to talk about today is like useless in practice because we don't know how to do that. But we can do one tweak to it next week that makes it useful. So. Yeah, so here to get this theoretical line here, we'd have to know the mean and standard deviation of this population, which we in practice don't know. Okay, so yeah, so the upshot here is that if we can, we're just gonna assume at this point that the sampling distribution of our means, which is this thing down here, right, is a normal distribution, and so we're gonna build tools for doing things based on that assumption. And again, that assumption is a pretty general one. It doesn't matter that much what the population distribution is, that usually the sampling distribution of the mean is going to be normal. Really, the only time this kind of assumption is going to break is if the population is very non-normal and our sample size is really tiny. So you can see here, like this is a, so yeah, here's a really weird looking population, and I'm only drawing 2 samples. And here is our sampling distribution of the mean, which is not that normal, right? It has like this weird truncated cutoff, and it's like not symmetrical, and right. So this does break down with really tiny samples, but it converges pretty fast. So you can see here, even with this pretty weird distribution, as soon as we get up to like even like a sample size of like 6 or 8 or so, we pretty much have a normally distributed sample mean. So almost any like practically interesting data set. So if we have a data set of 2 values, like we're not going to be able to do interesting inference anyway. That's kind of stats is not going to help, is not going to save us in any way there. So if we have any sort of reasonably sized data set, usually this converges quite quickly to this normally distributed sampling mean. Okay. So one immediate way we can use this is to do null hypothesis testing, right? So if we, so remember the goal for null hypothesis testing is we're going to assume that the population has some null uninteresting distribution, and then we're going to ask whether it looks like our sample could have come from that uninteresting distribution. And so the way we've done this so far is like, so at least one way we talked about doing this is is just simulating from some null distribution. So for example, in like the schizophrenia example from last week, we had a null distribution, which is that the chance of someone being diagnosed is just at some base rate, which is like the national base rate. And then we wanted to see whether those simulated null samples looked like our real sample or not. So that's one way to do this, but what the central limit theorem tells us is that we can actually just write down what this null sampling distribution looks like. We don't have to simulate it. And so what this tells us is that if we know the mean and standard deviation of our null distribution, then we can, and again, this is going to be like sort of assumptions that we're making, then we can write down what the sample, the distribution of sample means should be under that assumption, and then we can compare the actual thing we got to that normally distributed sample mean distribution. Right, so what we're going to do is take what we actually got, which is x bar, that's our actual data, and then we're going to compare it to this normal distribution. And we talked last week about, or on Tuesday, about a way to do this, which is to convert it to a z-value, meaning we're going to ask how many standard errors away from the mean is our sample data. Right, the central limit theorem tells us that the samples from this null distribution, sample means from this null distribution, should usually be pretty close to mu. Right, at most they're going to be 1 or 2 standard errors away, where the standard error is this sigma over square root of n piece. And so if our x bar is more than 2 standard errors away from the mean, then that means that it was pretty unlikely to have come from that null distribution, and we would reject the null hypothesis as a plausible explanation for our data. So let's walk through an example of this. So let's assume that our null hypothesis is that the mean is 2 and the standard deviation of this null population is 3. And so again, like I was saying, this assumption here is a pretty reasonable one. Usually we're going to have some null hypothesis that comes from some theory we're trying to test. Very often it'll be 0, right? That our null is going to be that there's like no difference between groups or something like that. We might have, or it might be something like a base rate in the general population, something like that. So this part is fine. This thing of having to make an assumption about the standard deviation of the null population is a weird thing that we don't want to do, and so we'll figure out how not to do that on Tuesday. But this overall is not that weird of a thing to do. This is not actually data, right? This is just, we're making a null assumption here. We're writing down what our null hypothesis is, and our null hypothesis is that the samples from our population should have a mean of 2 and a standard deviation of 3. And so we actually collect our real data, and the mean in our real data is 2.75. And so what we'd like to know is that weird or not, right? Is 2.75 a likely thing to happen when we collect 25 observations from this null distribution or not? and I don't think like you can just eyeball this. I think this is basically why we need to do some math and stats, is to say, is that like a surprising result or not? Is that something that is a likely sample we would have gotten out of this null distribution or not? Okay, so here we're just going to assume that the population is normally distributed. Again, this is actually like a little bit stronger of a assumption than you really need. We could also, most distributions will converge pretty quickly to normally distributed sampling mean distributions anyway. Okay, so what we can now just write down via the central limit theorem is we can just write down what this sampling distribution of the mean looks like, right? So our null hypothesis is that the population mean is 2. And so the central limit theorem tells us that our samples should also be centered around 2. So that's pretty easy. The central limit theorem also tells us that the standard deviation of these null samples, the means in the null samples, should be 3 divided by the square root of 25, and which is 0.6. Right. So what this tells us is that if we take 25 values from our null distribution with a mean of 2 and standard deviation of 3, and we take the average of those 25 numbers, the averages of that average of 25 numbers should be somewhere in the middle of this thing here, right? The average of the 25 numbers should be normally distributed around a mean of 2 with a standard deviation of 3 divided by the square root of 25, which is 0.6. Right, so what this tells us is that the most likely mean we're going to get is 2, which is the right one. But we could also get stuff that's up to sort of like 1.2 or so in either direction, right? So remember, for normal distributions, most of the normal distribution lives within 2 standard deviations of the mean. And so here, 2 standard deviations is 1.2, right? 2 times 1.6. So, okay, and then we can look at, so here's the actual number we got was 2.75, which is over here. So we're going to compute the p-value in a second, but just intuitively looking at this, you should see that it doesn't seem like our sample is that interesting, right? The number we got is a plausible one that would occur frequently under the null hypothesis, right? What this tells us is that if you draw 25 samples out of this null distribution with a mean of 2 and standard deviation of 3, it's not really that surprising to get something that's 0.75 away from 2. In fact, it could go all the way up to like, even if this was about 3, it still wouldn't be that surprising. Okay, so now we're going to write down the p-value. I'm just going to go through one more time what a p-value is, since we haven't been doing them recently. So the mean is never going to be exactly the sample mean, which is not surprising, but right, what we want to know is what's the chance of getting a gap between our null assumption and what we saw that's at least as big as the one that we observed. And so, right, the way to write this down in terms of conditional probability is like this, right, which is that, and this is sort of the way to read this, right, is that the p-value is the probability that a random outcome from our null distribution is going to be at least as far away from the population mean as what we actually saw. And this is all conditioned on the null hypothesis being true. So we're going to assume the null hypothesis is true. That's what the little bar H0 means on the right-hand side here, right? We're just going to condition into that universe where the null hypothesis is true. And we're going to ask, in that universe, how often do we get sample means that are at least as far away as what we actually got in our real data? And if we very often get sample means that are farther away from the population mean than our real data, that means our real data is not that interesting, right? It's pretty easy in this null universe to generate samples that have means that are at least 0.75 away from 2. So, right, again, the pieces of this, right, this is the given that the null hypothesis is true, right? And so we don't actually know what the population mean is here. What we're doing, this p-value is we're making this assumption that the mean is the population mean is our null hypothesis, right? That's the way we're able to like figure out this sampling distribution, is we're conditioning on that the null hypothesis is true, and that's going to let us write down what the sampling distribution is. This red box here is something that we actually measure right? So we know both of these things. So x bar is our actual measured sample mean. That's just a descriptive statistic of our data. And the mu here is our assumption about the null mean, right? That mu is the mean of our null hypothesis. So that's also a number that we know. That's coming from some like prior theory that we have or something, right? That's not a measured thing. It's not, this mu is not like the actual mu of the population, right? We're just living in this null universe where we know what the population distribution is because it's the null distribution, right? So this thing is just a number. X bar is a number, mu is a number. We can just subtract those two. This thing here is a random variable, which is if we draw a null sample from our null population and take the mean in that null sample, how far away are those means from 2? Right, so mu is 2 here. X null is a random variable though, which is it's probabilistic that depends on the sample that we draw. And so what this probability is asking is how often do we get samples that are at least as far away from the null mean as our actual data is? Yes.
So if you have just the one random x null, how does that show us how often, right? Doesn't that just show us one example?
So x bar is our real data that we have one of. X null though is not a number. X null is this distribution. So X null is the distribution that's coming from the central limit theorem, right? But the central limit theorem tells us that X null is centered. It's this normal distribution that's centered on mu and has this standard error associated with it. So this is the randomness in this thing is coming from X null, which is not a single value. It's this whole distribution of values.
So then which was the one that you said you just take a number?
So the mu, yeah. So the things that are going in here is so mu is just 2 here, right? Which is this is mu like given the null hypothesis, right? So the population, if we assume the null hypothesis is true, then we know the population mean because we're just assuming it, right? This is just kind of like circular. This thing, right? This x bar is also a number that we know. This is something that we just measure in our data. This x null thing, though, the x null thing is the weird thing, which is this, which is, right, this is x null, which is that if we take 25 samples from our null distribution and take their mean, what kind of values do those means have, right? And the central limit theorem tells us that they're centered on 2, and they have this standard error, which is 3 divided by the square root of 25. Right? 3 here again is just like an assumption that's coming from this conditioning. We're just assuming that that's the null distribution. And 25 is the number of things in our data set. Right? So the x null is this whole distribution of values, which is a probabilistic random variable. And that's where the p's are going to come from here. Right? That's the only thing that's uncertain in this probability equation is what value x null has. And so, yeah, x null is again, the way we've been doing this in the past is that we've been generating this x null from like simulations or permutation tests. Right? We've been using permutation tests to generate like thousands of these things and kind of get a histogram here. And now instead of a histogram, we're actually writing down like an equation for this line that doesn't require us to do any actual work with numbers. Right? That we're just using the central limit theorem to say that this is going to be a normal distribution with this particular mean and this particular standard deviation. Part of the reason that this is such a big piece of traditional statistics is just that prior to like 20 years ago, it would have been really hard to do the permutation tests and things like that, but it was really easy to write down the math for this. So some of it was just out of necessity, right? Doing it this way doesn't require you to use a computer. So to some extent, this is just sort of a leftover piece of that, but it's also, I think it is interesting to understand, right, that these null distributions we've been generating, we can actually predict what they're going to look like before we even run any simulations. Okay, so in this data here, right, we're 0.75 away from our null hypothesis, and so now what we need to compute here is how in this distribution of the null sampling means, how often do they have means that are even bigger than 2.75? And so the easiest way to do this, and again, this is sort of the traditional way to do this pre-computers, is you convert this into a z-score, right? And remember, the z-score is basically asking how many standard deviations away from the mean are we. So here, the standard deviation is this standard error thing, which is 0.6. And so we're like, right, 1.25 standard deviations away from the mean. And so what people used to do is you would look up, and I think there still is one maybe in the back of the stats book, there's like a table you could look up of what the p-value this is. Nowadays you would probably just like put this into R, so there's an R, you can either use the integrate function that we've been using in the labs. There's also this xp norm function in R that does the same thing, but you just plug in this z-score and then it pops out a p-value, right? And so what this p-value is just the area of the curve, under the curve that's above x bar, right? It's the probability of getting a null sample, getting a mean in a null sample that's at least 2.75. And right, so what this tells us is that this is not that surprising, right? So we are like bigger than null is not a good explanation for our data, right? It seems like, but essential limit theorem tells us that being 0.75 away from our hypothesized null mean here is not that interesting. Instead of 25 samples, we had 100. And now we could ask, right, is getting 2.75 in this case more impressive? And the answer is that it is, right? And the reason that it's more impressive is because the standard error is now 3 divided by the square root of 100, which is 0.3, right? What this is telling us is that if you take 100 samples out of this null distribution with a mean of 2, that the mean of those 100 numbers should be pretty tightly centered around 2, right? You should only be able to get maybe about 0.6 away or so from that true null mean because the sample is so large. And so if we compute the z-score in this case, the size of the gap is still 0.75, right? But now the denominator of our z-score is 0.3 instead of 0.6. And so now our z-score is twice what it was before. So now even though we haven't actually moved, we're now 2.5 standard deviations away from the mean because the standard deviation has gotten smaller, right? So between these two slides here, right, x bar didn't actually change, right? All that's happened here is that the sampling distribution has gotten tinier, has gotten thinner because the sample size has gotten larger. And so, right, again, we could look up in a table or use xp norm or use integrate or whatever. And what this tells us is that that less than 1% of the time you'd be able to be this far out in the tail if the null hypothesis is true, right? And so in this case, we would reject the null hypothesis. And so, right, one of the key points here is that if the null is 2 and we get a result, we get a sample mean of 2.75, whether or not that's interesting depends on a couple other things, right? It depends on what the standard deviation is in the population, and it depends on how big our sample was. And so, right, in the second case, we didn't change the numerator here, but we did change the denominator, right? We did change the sample size. Another thing here that could change is if the population standard deviation was a lot smaller, that also would make the standard error smaller and make this 2.75 more impressive. Any questions? Okay. So one thing that I briefly mentioned before, I'm going to now talk in a little more detail about, is one-tailed versus two-tailed tests. And so in this example so far, we've been looking at changes in the null in a single direction, meaning that we've been asking, we got 2.75, and we've been asking basically how much area is like below us, right? And so, we've been asking how much area is below us, and so, right, we've just been interested in asking how often do sample means get larger than 2.75. But it might often be the case that we don't actually care about a directional hypothesis like this. We actually care about deviations in either direction from our null hypothesis, right? So if you're testing a drug, for example, and we have there's some like baseline rate from placebo of how many people we expect to get better. We are hoping that in our sample we have more people getting well compared to the placebo. But we'd also be really interested to know if our intervention's actually making things worse, right? We also want to know if there's a deviation in the opposite direction. And we'd like our test to reflect that, right? We'd like a test that is telling us, does it look like the null hypothesis is a good explanation for our data in either direction, right? That we're interested not only in null samples that are bigger than us, but simply ones that are bigger than us in absolute value. Right? How often is it that we get a deviation this large in either direction from the null hypothesis? And so this will change our p-value, in this case in a very simple to compute way. So, right, so let's look at this example here. So this is an example we have a measured x-mean of 3. And if we wanted to compute a two-tailed p-value, what we'd be looking for is how often in this null sampling distribution, which again, the null sampling distribution has a mean of 2, standard deviation of 0.6. How often do you get values which are more than 1 away from the population mean in either direction? Right? Our sample mean is 1 away in the positive direction, but we're just asking how often do you get at least 1 away in either direction? Mean happens about 10% of the time, so we're not going to say that our data is not coming. The 1 and 2 tail tests are always just going to be like this, where one is just double the other, right? Because the normal distribution is symmetrical, and so the area that's under 1 tail is going to just be half the area under 2 tails, right? And so the 2-tailed p-value is just going to be twice the 1-tailed one. So you might come up with an idea here, right? If our goal is to, like as researchers, is to get small p-values and get published and stuff, then we should just always use one-tailed tests, right? We could just get our data, we see which direction our sample mean ended up on, and then just run a one-tailed test in that direction. So if we run our sample and it looks like the drug is helping people, then we run a one-tailed test for helping. If it looks like our drug is hurting people, we run a one-tailed test for hurting, right? And then we'll always end up with like half the p-value of a two-tailed test. Does this seem like a good idea or a bad idea? Yeah, so this is a bad idea. We're going to talk in a few weeks about why, specifically, all the reasons why it's bad. But this is not. If we use our data to pick our hypothesis test, then we'll end up with invalid p-values. And so, yeah, we'll again talk about this later. But if we had done my idea, we basically would be getting wrong answers. We would be incorrectly rejecting the null too often if we did things that way. Right, that if we really don't have if deviations in either direction are potentially interesting to us, which is probably about like at least 90% of the time the case, right, the deviations from the null in either direction are interesting, then we really should be running a two-tailed test. That we really should be, right, we want to compare to nulls to both of the tails here because we don't know which tail we're going to end up in. And so it's unfair to like pick the tail we want to compete in after we know which tail we're actually in. Yeah.
Then why not always do a two-tail?
Yeah, so you could always do a two-tail test, and that's, I think, actually the right answer most of the time. A one-tail test is appropriate if really only one direction is interesting, which is the case sometimes. So it might be the case, for example, that there's like you have people trying to make some kind of guess, and there's like a chance level of guessing, and it's impossible to be guessing less than chance, but maybe if you have information, you could guess more than chance. Then in that case, you could use a one-tail test because like it's like literally impossible for people. We know it's not possible for things to be less than chance, and so we're only testing. We sort of know we're never going to compete in that side of the tail, and so it's fair to ignore it. But yeah, it is the case. Usually, you should really be using two-tailed tests. Of course, the reason people don't, again, is because of this region of you can cut your p-value in half if you do a one-tailed one, and so this is one of the many ways people try to fudge p-values, which we'll talk about in a few weeks. Okay, so the danger here, well, sort of the whole point of having a statistical threshold for these p-values is because we want to limit the number of times when we're wrong. And there's actually multiple ways we could be wrong in these kinds of statistical tests. And so people often draw just this kind of 2x2 grid here. So the columns of this grid are the actual state of the world, which is the null hypothesis is true or the null hypothesis is false. And so we never actually know which column we're in here, right? That's part of the point of doing the statistics is we're trying to get some evidence of which column we're in.
Isn't this type 1? Is this type
We'll get to that in 1 second. That's right. And on the rows here is like our actual statistical test, which is the p-value that we got. Is it a below or above our threshold, this alpha threshold, which again is usually 0.05, but we might set differently in different cases. And so what we hope happens is that we end up in one of these two squares, which is that either our test gives us a big p-value and we fail to reject the null, and that was actually the right decision. The null is actually true here, and it's a good thing we didn't reject it. Right? So that we call a true negative, meaning we thought that there's nothing interesting in the world. That's what negative means here, right? We thought there's nothing interesting in this data, and we're right. The null hypothesis is true, nothing's interesting. Where we really would like to be, of course, is down here in the bottom right, which is that in our data we got a small p-value, indicating that the null is not a good fit for our data. And we conclude that we have a positive result, meaning that there is something interesting in this data, and we're right. The null hypothesis is false. There is something interesting in the world, and we were correct in making that inference. Right, so we'd really like to be down here in the bottom right. Top left also is not too bad. At least we know something about the world that we didn't before, right? It's just we learned the world is not interesting, which is maybe not that exciting, right? But at least we're consistent with the world, right? Where we don't want to be is in these other two boxes. And so this bottom left one is a false positive, which is where we get a small p-value. We say the world is interesting, but we're wrong. The null hypothesis is actually true. Right? False positive is when we say there's a positive result, meaning that there's something interesting happening in this data, but we're wrong. The top right here is a false negative, which is where we get a big p-value, and we say, well, maybe the null hypothesis is true. It doesn't seem like there's anything interesting in this data, but we're wrong. There actually is something interesting in this data. We just missed it. Right? Maybe we just got unlucky with our sample. Maybe our sample wasn't big enough. Maybe there was too much noise in our measurement, something, right? And so, false negatives are bad in the sense that we missed something, but at least we're not trying to claim something false about the world, so it's not too bad. Right? False positives is really the kind of most dangerous of the 4 boxes here, right? Is where we say we discovered something, but we didn't actually do it. And so, one thing to notice here is that the setting of alpha controls where we end up here, right? So the p is coming out of our statistical analysis. The only real thing we have control over here is this setting of alpha, which is our threshold for when are we going to reject the null hypothesis. How small does p have to be to reject the null hypothesis? And so if we're really afraid of this bottom, if we're really afraid of this square here, one way we could try to get out of that square is by making this alpha really small, right? So if we make alpha all the way down to, there's been calls in the statistical literature that alpha really should be 0.005, right? 10 times smaller than what we usually use. So if you use 0.005, it means that it's pretty likely, it means that the chance of being in this bottom row at all is a lot lower, right? It's a lot harder to get into this bottom row, and therefore it's a lot harder to end up in this bad square. It does mean you're going to end up in this top row a lot more, and that you're going to end up in this false negative square a lot more often, right? But maybe that's okay, at least for like basic science research. Maybe false negatives are kind of okay. It just means we failed to figure something out, whereas false positives are really bad because then it means we're claiming that we know something about how the world works, which is not true, and it's going to like mislead our further research and things like that. Of course, this also depends on the situation. That it might be, let's say you're testing people for a disease that we're worried is spreading, and then there a false negative is potentially very bad. False negative is where someone has the disease and you fail to see it, and so in that case you actually might want an alpha that's like 0.2 or something, or even higher, right? That if there's any evidence in this sample that something is going on, we want to react to it. And sometimes it'll be a false positive, but that just means someone got some extra medical treatment they didn't need. Whereas false negative means that they're failing to get some really critical medical treatment. So yeah, there was a question before about this type 1, type 2 error stuff. So in some statistics books, I think it's in ours too, they call these t-squares type 1 and type 2 error. I think this is total nonsense. Like, there's no reason that one of these is 1 and 2. They have perfectly good names, which is false positive, false negative, so I will not use this. I honestly think it's like some kind of weird statistics gatekeeping to like see if people know what the square is. I don't know, but I'm not going to use that terminology. Okay, so yes, as we said, right, we want to stay out of these error boxes, however we label them, and the way to stay out of this box again is to set a conservative alpha, right? That we don't want to reject the null hypothesis unless we're really sure that it's bad. And so the way to stay out of this box, we haven't really talked about too much yet, but right, what we want to stay out of this box, what we want to make sure is that if the null hypothesis is false, that our p-value is small, right? That if the null hypothesis is false, we can actually tell in our data that it's false. And so this basically requires our experiment to be well powered, which means, I mean, the main thing it means is something about sample size, but it also means something about how good our samples are. So if we're making a measurement that has tons of noise in it, for example, it's going to be really hard to see what we're doing, right? And so you could think about this sampling mean here. The distribution of the sample means here. We like the distribution of the sample means under the null to be really small. That way, it's really easy to detect deviations, right? So if like in this example here, if the sampling distribution under the null is really wide, then it's really hard to get a good p-value. Our real data has to be like way out here somewhere in order for us to actually say that it's good. But if our sampling distribution were really tight around the mean here like this, then we can be like very sensitive, right? That if our real data is even like here, we'll know that it's not coming from the null, right? So to stay out of this box, what we want is our sampling distribution to be really tiny. And so, so let's think about the width of this distribution. The width of our sampling mean distribution has two things in it, right? Which are what? What controls the standard deviation of the distribution of our sample means?
The number of values?
Yeah, yes, the bottom one is that, right? It's varied in. And then what's on the top?
The population standard deviation.
That's right. So there's two. So if we want this thing to be tiny, there's sort of two things we can do. One thing we can do is just make n really big, and again, this formula also assumes again that we're taking unbiased random samples from the population, which again is always never exactly true. But if we have a way of getting lots of unbiased samples, that works. The other thing we can try to do is make this smaller. And so we haven't really talked about this too much yet, but like this sigma, it's partially a property of the world, like just how variable the thing is that we're trying to study. Maybe there's lots of individual differences in this thing. But another thing that comes into this is how accurately we can measure it, right? So remember the population distribution is like if we take one sample from the world, how much variability is there in that sample? And that variability comes from both actual variability in the world that we don't have control over, and the variability we're adding as experimenters, right? That if we bring subjects into the room and then for each person we blast some different song at them while they're doing the experiment, it's going to add lots of variability into their responses that's not like inherent in the task, right? It's something that's happening based on the way we're measuring it. So if we want to have what we'd like to have is this nice tiny sampling mean distribution. So we want to try to make this thing big and make this thing small. And again, it depends on the situation, like which of those things makes more sense to do. In theory, at least, you can always do this if we have enough money and time and a way of like collecting unbiased people. This might be a little bit harder. Part of this has to do with variability in the phenomenon you're studying, which you don't have control over. And part of it has to do with errors in the way you're measuring it, which might have to do with your experimental design. It might have to do with like the physical apparatus you're using. So if you're measuring reaction times, people that are really into measuring reaction times in psychology have these special keyboards that like are super accurate at measuring millisecond reaction times and stuff, right? So that would be a way of bringing down this thing. And so the smaller we can make this standard error, the more we can stay out of this box up here, right? The more likely it is that if the null hypothesis is false, we will correctly end up down in this box down here with a small p-value. Yes?
How should we quantify like how far the standard deviation drops by making changes to our experiments?
Yeah, so I mean, you can just look. Our best estimate of the population distribution is just the distribution of the individual samples in our data set, right? And so that's usually what people do, right? So you just collect a data set using one keyboard, collect a data set using a different keyboard, and like look at the width of the, right, the amount of variation that you're getting. But yeah, but it is, so in general, we might have some ideas of how to bring this down. In terms of actually estimating this number is going to be really hard because some of it depends on the population standard deviation, which we don't know because we don't know the population, right? So we usually can't actually estimate this number, and so we're going to talk about on Tuesday how to get around estimating this numerically. But we can still think about ways of, at least we have ideas about how we'd make it smaller, even if we don't know what the actual number is. Okay, any other questions? All right, so the last thing we're going to talk about is confidence intervals. So we already have talked about a way to get confidence intervals, which is using bootstrapping, right? So if we want a confidence interval for the mean, for example, we could collect bootstrap samples, see how much variability there is in those samples. But the essential limit theorem tells us that whatever the true population mean is, which is mu here, then the sample means almost always are going to be within 2 standard errors of that population mean, right? Technically, it's 1.96, right? So 1.96 standard errors, that is 95% of the area of a normal distribution. And so what this, so here's like, well, there's this SXC norm function in R makes a little plot of this. And so the idea here is that whatever the sample mean, the population mean is, so in our population there's some mean here, and what the central limit theorem tells us is that that's going to generate a sample mean, which is like somewhere in this range, which is like mu minus 2 sigma over square root of n up to mu plus 2 sigma over square root of n. Right, so the population, the central limit theorem tells us that the distribution of our sample means are going to mostly be here. And so what we're going to try to do with this confidence intervals is to run this backwards. So of course in reality, things are not working this way. In reality, what's happening is we have a single sample mean, which we measured, and we want to make some estimate of what's going on in the population. And so what we could think is we could think about what population means would be likely to lead to our sample mean, right? And so if we had a population mean that was over here, for example, then that maybe could have just barely, right, that maybe could have generated us, this one over here. If we had a population mean over here, that also maybe could have like just barely generated us, right? But means that are like farther to the left than this or farther to the right than this, their sampling distributions don't overlap with us, right? Not in a meaningful way. So what this tells us is that if our sample mean is here, that basically gives us a range for what likely population means could have generated us, right? Which is that population means anywhere up here, their sampling distributions overlap with us, but population means that are too far away, their sampling means, the distribution of sampling means don't overlap with us, right? So we can basically just like reverse this logic of this here and say that if we have what we've measured as our sample mean, then the true population mean is probably within 2 standard errors of us, right? We don't know where it is up there, but any population mean within 2 standard errors of us could have plausibly generated our data that we saw. Right. So what this means is that we can just write down our confidence interval. We don't have to do any bootstrapping. It does require us to know standard deviation of the population, which we don't know, so this doesn't 100% work, but we'll fix that on Tuesday, right? But if we knew the population standard deviation and we know the number of samples in our data set, which we usually do, then we can just plug into this formula to get confidence intervals. Right, so let's give an example here. So let's say we have the standard deviation in our population. Let's just assume it's 3, and we have n equals 100. That tells us that the standard error is 0.3. And so what that would tell us is that if what we measured in our sample is 2.75, then the likely population means that could have generated our sample are something like plus or minus 0.6 away from that. Right, so our the 95% confidence interval here is between this 2.162 and 3.338. Right, those are the population mean values that would have been likely to generate our sample mean. And so the little drawing here, right, is showing it's showing a normal distribution that's centered not on the population but on ourselves, right? The distribution here is centered on the x we actually got, which is a little bit backwards of the logic we've been doing so far, right? But what this is saying is that if we look at the sample we actually got and we look at which population values are likely to have generated us, that also yields a normal distribution with the same shape. And so another interesting connection here is that this confidence interval also tells us something about the p-value, right? They're kind of related to each other, which is that because this confidence interval doesn't overlap with our null hypothesis, which is 2, right? Remember the lower edge of this this confidence interval was like 2.1 something. So what that tells us is that if we ran a two-tailed test here, that we would get a p-value that's less than 0.05. Right, the confidence interval, the likely population means don't include 2, right? Which tells us that our null hypothesis is probably not true, right? That whatever the population mean is, we're pretty sure it's like between 2.1 and 3.3. We don't think it's 2, right? And so this is a nice thing about confidence intervals is that they sort of give you both answers, right? They tell you both. They give you an estimate of what the population mean is, which you can also use to see whether the null is actually in that set or not. So the reason we don't always just do this is again, we usually do want like a specific p-value, and so getting a specific p-value out of this method is like a little harder. So if we want an exact number for p, then we would do the null hypothesis testing, where we right, again, it's a very similar idea. All we're doing is just checking to see how many standard errors away from the null are we, and what's the p-value associated with being that many, with that z-value of being that many standard errors away. You could also here, this is just for 95% confidence intervals, but you could do this for maybe you want a 99% confidence interval. You want to be really sure that our population mean is included in our interval. So what would change here if we wanted to have a 99% confidence interval? What would we have to do differently? Well, maybe I should test this first. If we want a 99% confidence interval instead of 95, is our confidence interval going to get bigger or smaller? Here's some mixed results. So let's think again about what confidence intervals are. So so a 95% confidence interval is that we observe our sample, and we want a range of population. We want to give a range of guesses about the population where we're right 95% of the time, meaning that the true population mean is inside that range we give 95% of the time. If we want to be right 99% of the time, we're going to have to be a little more liberal in our guessing, right? So if we want to be right 100% of the time, then what we can do is just guess that that mu is somewhere between negative infinity and infinity, and then we're right 100% of the time, right? It's not very useful, but we'll always be right, right? If we want to be right, so if we want to be right 99% of the time, we're going to need to have a bigger interval than a 95% confidence interval, right? We're unwilling to be wrong. We're only 1% of the time do we want the true mean to fall outside what we guessed. And so what it means is that we have to be more uncertain, right? We have to give an interval that's big enough
so that only 1% of the time the true population mean is outside that interval. Right? So a 99% confidence interval is going to be bigger than a 95% one. If you only wanted like a 10% confidence interval, we could just guess a tiny, tiny little range around our mean. We'll be wrong like most of the time, but that's fine, right? So what would we want to? So what would we have to change here? Or I guess another way of asking this is like, in the equations here, which of these numbers have to do with the fact that we picked 95% specifically? Yeah, that's right. So in the equation here, right, this is just the sample mean that we measured. That doesn't have anything to do with confidence intervals. This 0.3 is the standard error we calculated from our null assumption and this equation. That has nothing to do with confidence intervals, but this thing does. So this 1.96, that's the z-score that corresponds to 95% area under the curve, right? 95% of the normal distribution is between negative 1.96 and positive 1.96. So if we wanted a 99% confidence interval, we'd have to make this number bigger. I don't actually know what it is off the top of my head. It's probably like 2 point something, right? Which is that you'd have to go something like maybe, you need a z of something like 2.5 or so to say that you'd need to, so that 99% of the area of the normal is between plus or minus that z-score. Right, so if we want to have a 99% confidence interval, we'd have to use a bigger number here instead of 1.96. That's going to make this thing smaller and this thing bigger, right? Putting in a bigger number than 1.96 is going to make the confidence interval larger. It's going to change how far away from the mean, how far away from the sample mean we're guessing the population mean could be. Right, so so again, this thing is just our measured data that we don't have control over. This thing is going to be set depending on whether we want, what kind of confidence interval we want, 90%, 95%, 99%. And then this thing here, this 0.3, again, is coming from the standard error, which we also do have some control over, right? We could, if we want a smaller confidence interval, we could collect more subjects. That'll make this thing smaller, and that'll make our confidence interval smaller as well, right? If we collect more subjects, we can be more confident that the population mean isn't that far away from where we really are, right? So I think it's important to try to keep track of what stuff we have control over and don't as experimentalists, right? And so we don't have control over where the mean comes out, but we do have control over, right? This 0.3 depends on our experimental design, both in terms of how cleanly we're measuring what we want and how big our data set is. And then this 1.96 also we have control over, but it has nothing to do with our experiment. It has to do with what kind of conclusion we want to draw. Do we want a 95% confidence interval? Do we want a 99%? It again has to do with this trade-off of like false negatives and false positives. How willing are we to miss real stuff sometimes or accidentally say there's something when there isn't? And that again is also a choice that we're making that depends on the situation. Okay, so last slide here that we already mentioned is that we unfortunately almost never can actually use this because we don't know this. We don't know this number to plug it in, and it's also not. You might think maybe a way we could cheat here is just estimate this with the sample standard deviation, but that's close to the answer, but you can't just plug that in. That's not going to totally work because our estimate of the sample standard deviation is not going to be exactly right. So we're going to talk about this on Tuesday. This is probably the most famous statistical test in psychology we'll talk about on Tuesday as a way to get around having to know this number. And we'll yield a test that's very applicable to tons of experiments you'd actually run. Any else questions? All right, homework 6 is due on Tuesday. I apologize, I forgot to turn it on until this morning, but I don't think anyone was working on it anyway. But it is up online and it's due in class on Tuesday.